Chapter 2 of How It Flies, or Conquest of the Air. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Tom Penn. How It Flies, or Conquest of the Air, by Richard Ferris. Chapter 2 The Air. The air about us seems the nearest approach to nothingness that we know of. A pail is commonly said to be empty, to have nothing in it, when it is filled only with air. This is because our senses do not give us any information about air. We cannot see it, hear it, touch it. When air is in motion, wind, we hear the noises it makes as it passes among other objects more substantial, and we feel it as it blows by us, or when we move rapidly through it. We get some idea that it exists as a substance when we see dead leaves caught up in it and whirled about, and, more impressively, when in the violence of the hurricane it seizes upon a body of great size and weight, like the roof of a house, and whisks it away as though it were a feather, at a speed exceeding that of the fastest railroad train. In a milder form, this invisible and intangible air does some of our work for us in at least two ways that are conspicuous. It moves ships upon the ocean, and it turns a multitude of windmills, supplying the cheapest power known. That this atmosphere is really a fluid ocean, having a definite substance, and in some respects resembling the liquid ocean upon which our ships sail, and that we are only crawling around on the bottom of it, as it were, is a conception we do not readily grasp. Yet this conception must be the foundation of every effort to sail, to fly, in this aerial ocean, if such efforts are to be crowned with success. As a material substance, the air has certain physical properties, and it is the part of wisdom for the man who would fly to acquaint himself with these properties. If they are helpful to his flight, he wants to use them. If they hinder, he must contrive to overcome them. In general, it may be said that the air, being in a gaseous form, partakes of the properties of all gases, and these may be studied in any textbook on physics. Here we are concerned only with those qualities which affect conditions under which we strive to fly. Of first importance is the fact that air has weight. That is, in common with all other substances, it is attracted by the mass of the earth exerted through the force we call gravity. At the level of the sea, this attraction causes the air to press upon the earth with a weight of nearly 15 pounds, accurately 14.7 pounds, to the square inch, when the temperature is at 32 degrees Fahrenheit. That pressure is the weight of a column of air, 1 inch square at the base, extending upward to the outer limit of the atmosphere, estimated to be about 38 miles, some say 100 miles, above sea level. The practical fact is that normal human life cannot exist above the level of 15,000 feet, or a little less than 3 miles, and navigation of the air will doubtless be carried on at a much lower altitude, for reasons which will appear as we continue. The actual weight of a definite quantity of dry air, for instance a cubic foot, is found by weighing a vessel first when full of air, and again after the air has been exhausted from it with an air pump. In this way it has been determined that a cubic foot of dry air, at the level of the sea, and at a temperature of 32 degrees Fahrenheit, weighs 565 grains, about 0.0807 pounds. At a height above the level of the sea, a cubic foot of air will weigh less than the figure quoted, for its density decreases as we go upward, the pressure being less owing to the diminished attraction of the earth at the greater distance. For instance, at the height of a mile above sea level, a cubic foot of air will weigh about 433 grains, or 0.0619 pounds. At the height of 5 miles it will weigh about 216 grains, or 0.0309 pounds. At 38 miles it will have no weight at all, its density being so rare as just to balance the earth's attraction. It has been calculated that the whole body of air above the earth, if it were all of the uniform density of that at sea level, would extend only to the height of 26,166 feet. Perhaps a clearer comprehension of the weight and pressure of the ocean of air upon the earth may be gained by recalling that the pressure of the 38 miles of atmosphere is just equal to balancing a column of water 33 feet high. The pressure of the air, therefore, is equivalent to the pressure of a flood of water 33 feet deep. But air is seldom dry. It is almost always mingled with the vapor of water, and this vapor weighs only 352 grains per cubic foot at sea level. Consequently, the mixture, damp air, is lighter than dry air in proportion to the moisture it contains. Another fact very important to the aeronaut is that air is in constant motion. Owing to its ready expansion by heat, a body of air occupying 1 cubic foot when at a temperature of 32 degrees Fahrenheit will occupy more space at a higher temperature and less space at a lower temperature. Hence, heated air will flow upward until it reaches a point where the natural density of the atmosphere is the same as its expanded density due to the heating. Here another complication comes into play, for ascending air is cooled at the rate of 1 degree for every 183 feet it rises, and as it cools it grows denser, and the speed of its ascension is thus gradually checked. After passing an altitude of 1,000 feet, the decrease in temperature is 1 degree for every 320 feet of ascent. In general, it may be stated that air is expanded 1/10 of its volume for each 50 degrees Fahrenheit that its temperature is raised. This highly unstable condition under ordinary changes of temperature causes continual movements in the air, as different portions of it are constantly seeking that position in the atmosphere where their density at that moment balances the earth's attraction. Sir Hiram Maxim relates an incident which aptly illustrates the effect of change of temperature upon the air. He says, "On one occasion, many years ago, I was present when a bonded warehouse in New York containing 10,000 barrels of alcohol was burned. I walked completely around the fire and found things just as I expected. The wind was blowing a perfect hurricane through every street in the direction of the fire, although it was a dead calm everywhere else. The flames mounted straight in the air to an enormous height, and took with them a large amount of burning wood. When I was fully 500 feet from the fire, a piece of partly burned 1-inch board about 8 inches wide and 4 feet long fell through the air and landed near me. This board had evidently been taken up to a great height by the tremendous uprush of air caused by the burning alcohol. That which happened on a small scale, with a violent change of temperature, in the case of the alcohol fire, is taking place on a larger scale, with milder changes in temperature, all over the world. The heating by the sun in one locality causes an expansion of air at that place, and cooler, denser air rushes in to fill the partial vacuum. In this way winds are produced. So the air in which we are to fly is in a state of constant motion, which may be likened to the rush and swirl of water in the rapids of a mountain torrent. The tremendous difference is that the perils of the water are in plain sight of the navigator and may be guarded against, while those of the air are wholly invisible and must be met as they occur, without a moment's warning. Next in importance to the aerial navigator is the air's resistance. This is due in part to its density at the elevation at which he is flying, and in part to the direction and intensity of its motion, or the wind. While this resistance is far less than that of water to the passage of a ship, it is of serious moment to the aeronaut, who must force his fragile machine through it at great speed, and be on the alert every instant to combat the possibility of a fall as he passes into a rarer and less buoyant stratum. 3 properties of the air enter into the sum total of its resistance: inertia, elasticity, and viscosity. Inertia is its tendency to remain in the condition in which it may be, at rest if it is still, in motion if it is moving. Some force must be applied to disturb this inertia, and in consequence, when the inertia is overcome, a certain amount of force is used up in the operation. Elasticity is that property by virtue of which air tends to reoccupy its normal amount of space after disturbance. An illustration of this tendency is the springing back of the handle of a bicycle pump if the valve at the bottom is not open, and the air in the pump is simply compressed, not forced into the tire. Viscosity may be described as stickiness, the tendency of the particles of air to cling together, to resist separation. To illustrate, molasses, particularly in cold weather, has greater viscosity than water. Varnish has greater viscosity than turpentine. Air exhibits some viscosity, though vastly less than that of cold molasses. However, though relatively slight, this viscosity has a part in the resistance which opposes the rapid flight of the airship and airplane, and the higher the speed, the greater the retarding effect of viscosity. The inertia of the air, while in some degree it blocks the progress of his machine, is a benefit to the aeronaut, for it is inertia which gives the blades of his propeller hold upon the air. The elasticity of the air, compressed under the curved surfaces of the airplane, is believed to be helpful in maintaining the lift. The effect of viscosity may be greatly reduced by using surfaces finished with polished varnish, just as greasing a knife will permit it to be passed with less friction through thick molasses. In the case of winds, the inertia of the moving mass becomes what is commonly termed wind pressure against any object not moving with it at an equal speed. The following table gives the measurements of wind pressure, as recorded at the station on the Eiffel Tower, for differing velocities of wind. There follows in the text a table listing velocity in miles per hour, velocity in feet per second, and pressure in pounds on a square foot for a range of velocities from 2 to 100 miles per hour. In applying this table, the velocity to be considered is the net velocity of the movements of the airship and of the wind. If the ship is moving 20 miles an hour against a headwind blowing 20 miles an hour, the net velocity of the wind will be 40 miles an hour, and the pressure 4.8 pounds a square foot of surface presented. Therefore the airship will be standing still, so far as objects on the ground are concerned. If the ship is sailing 20 miles an hour with the wind, which is blowing 20 miles an hour, the pressure per square foot will be only 1.2 pounds, while as regards objects on the ground, the ship will be traveling 40 miles an hour. Systematic study of the movement of the air currents has not been widespread, and has not progressed much beyond the gathering of statistics which may serve as useful data in testing existing theories or forming new ones. It is already recognized that there are certain tides in the atmosphere recurring twice daily in 6-hour periods, as in the case of the ocean tides, and perhaps from the same causes. Other currents are produced by the Earth's rotation. Then there are the 5-day oscillations noted by Elliot in India, and daily movements more or less regular due to the sun's heat by day and the lack of it by night. The complexity of these motions makes scientific research extremely difficult. Something definite has been accomplished in the determination of wind velocities, though this varies largely with the locality. In the United States, the average speed of the winds is 9.5 miles per hour. In Europe, 10 1/3 miles. In southern Asia, 6.5 miles. In the West Indies, 6 1/5 miles. In England, 12 miles. Over the North Atlantic Ocean, 29 miles per hour. Each of these average velocities varies with the time of year and time of day, and with the distance from the sea. The wind moves faster over water and flat, bare land than over hilly or forest-covered areas. Velocities increase as we go upward in the air, being at 1,600 feet twice what they are at 100 feet. Observations of the movements of cloud forms at the Blue Hill Observatory near Boston give the following results. Stratus clouds at a height of 1,676 feet have an average speed of 19 miles per hour. Cumulus clouds at a height of 5,326 feet have an average speed of 24 miles per hour. Altocumulus clouds at a height of 12,724 feet have an average speed of 34 miles per hour. Cirrocumulus clouds at a height of 21,888 feet have an average speed of 71 miles per hour. Cirrus clouds at a height of 20,317 feet have an average speed of 78 miles per hour. In winter, the speed of cirrus clouds may reach 96 miles per hour. There are 49 stations scattered over Germany where statistics concerning wind are gathered expressly for the use of aeronauts. At many of these stations records have been kept for 20 years. Dr. Richard Osman, director of the Aerological Observatory at Lindenberg, has prepared a comprehensive treatise of the statistics in possession of these stations, under the title of Die Wind in Deutschland, It shows for each station and for each season of the year how often the wind blows from each point of the compass, the average frequency of the several degrees of wind, when and where aerial voyages may safely be made, the probable drift of dirigibles, etc. It is interesting to note that Friedrichshafen, where Count Zeppelin's great airship sheds are located, is not a favorable place for such vessels, having a yearly record of 24 stormy days, as compared with but 2 stormy days at Celle, 4 at Berlin, 4 at Cassel, and low records at several other points. In practical aviation, a controlling factor is the density of the air. We have seen that at an altitude of 5 miles the density is about 3/8 the density at sea level. This means that the supporting power of the air at a 5-mile elevation is so small that the area of the planes must be increased to more than 2.5 times the area suited for flying near the ground, or that the speed must be largely increased. Therefore, the adjustments necessary for rising at the lower level and journeying in the higher level are too large and complex to make flying at high altitudes practicable, leaving out of consideration the bitter cold of the upper regions. Mr. A. Lawrence Rotch, director of the Blue Hill Observatory, in his valuable book The Conquest of the Air, gives this practical summary of a long series of studious observations. At night, however, because there are no ascending currents, the wind is much steadier than in the daytime, making night the most favorable time for aerial navigation of all kinds. A suitable height in the daytime, unless a strong westerly wind is sought, lies above the cumulus clouds at the height of about a mile, but at night it is not necessary to rise so high, and in summer a region of relatively little wind is found at a height of about 3/4 of a mile, where it is also warmer and drier than in the daytime or at the ground. Notwithstanding all difficulties, the fact remains that once they are overcome the air is the ideal highway for travel and transportation. On the sea a ship may sail to right or left on one plane only. In the air we may steer not only to right or left, but above and below and obliquely in innumerable planes. We shall not need to traverse long distances in a wrong direction to find a bridge by which we may cross a river, nor zigzag for toilsome miles up the steep slopes of a mountain side to the pass where we may cross the divide. The course of the airship is the proverbial bee line, the most economical in time as well as in distance. End of chapter 2.